I will be discussing today on the moment distribution on sway frames, right? So basically, when you are when you use moment distribution to frames, right? For frames, right? So you can have either a non-sway or sway frame. So in the second video I did earlier, after the basic video, that contains a non-sway frame. But today we are going to discuss what is a sway frame. What is actually sway, right? So again, we need to understand what is actually sway means, right? So let me show you a quick video, right? To understand the concepts. So as you can see, right? So they just place some using springs, right? So that spring, why the spring? So always think that has some stiffness, right? So that's act as a column, and that's the beam member, right? So it's basically a frame, right? So you can see when a lateral load is applied, it horizontally deflects, right? So this joint horizontally moves in this way. So the entire frame, right? So what if they provide this is bracing, right? So you can see now if they start applying a load, can you see what happens? Can you see? So they provide a bracing to stop sway, right? So if they apply, this member will shorten, right? It is compressed. So this is going to push this way. So push this way means in this member that will have a tension, right? If you put the other way, it is reverse. This will have a compression and this will have a tension, right? So basically there are different methods to cause this stop this way and change it, right? So you can see now they are fixing it, right? So basically they are doing is they create a fixed support. Here it was originally a pin support. So we consider the fundamentals. It can rotate, right? Rotation degree of freedom is not restrained, but here it is a fixed one, right? Here you can see fixed one. So here also they are fixing it. So now what happens? This cannot rotate, right? So there's a restrained movement. So and that also a rigid joint. This joint keeps it 90 degrees, right? How? There will be a bending moment. Earlier there was only, right, a smooth joint where joints. So you saw that when a load apply, can you see the 90 degrees has changed, right? So it, joint can rotate. So this is a smooth joint, right? So the joint angle is now around 130 or 40 something, right? But if you apply a rigid joint, that does not change its shape, right? So it's like a fixed one, right? Fixed joint. So can you see it keeps 90 and strong support conditions, right? So there will also be bending moments, right? So there's a reason behind everything, right? So rather than watching a video, please check its why. It's a continuous joint and there's a fixed condition. Always try to interpret this, right? So why it happening? Why it's happening? So why it's not, right? So the sway action means completely this movement, right? So this movement, this horizontal, when a lateral load is applied, uh, this horizontal movement can be important, especially when you are considering the bending moments. Why? Because so it will cause an additional bending moments due to the P delta effect. So this is really, so this is frame, and so you have some lateral loading. So if it moves like this way, right? Right. So you can see now P is here, right? So this is sway. This is sway action, right? This is the sway action, right? So it has horizontally moved. So just think, if it was restrained in the horizontal direction, or else a pin support, right? Like this. Right. So the first thing is you need to determine, right? Is there, right? Is this frame can move horizontally? So this cannot move, right? If this try to move, this support will keep it, right? Keep its shape, and it prevents horizontal movement. This support as well, because degrees of freedom in this direction and this direction is restrained from this support. But here it is not. It cannot restrain this direction or the other way around degrees of freedom. So that this frame will sway, right? This frame will sway. So the first condition is the frame is allowed to move, right? So why does it move? It because it is allowed to move, right? So first you check that allowed to move, right? So there can be something like this. So if a load apply, this is allowed to move, right? So it can go in this way. So your frame would be something like this, right? But some frame like this, so here it's vertical direction is restrained, right? Even there's a pin support as this, it's non-sway, right? So first you should determine whether it is allowed to move, right? So then the second thing is, so this kind of frame, even it is allowed to move if you have the loading exactly at the middle, right? If you add the loading exactly at the middle, right? It's a special case. So this will not still, this will not move in horizontal direction, right? Still non-sway, but it's allowed to move, right? So no horizontal restriction, right? Allow no horizontal drop, allowed to move, but loading is symmetric, right? Symmetric and does not have does not have lateral forces. So if it has any lateral forces, this is definitely moving. So the second thing is lateral forces. It should be allowed to move first, right? Then if your frame have in lateral forces, so definitely it will move, right? So sometimes there are not any lateral forces. It's kind of like this. So think about this frame. There are no lateral forces. So in that case, this is not going to sway, right? So why? Loading is symmetric, right? So you can just see. But let's think about if your loading is asymmetric. So if you try this, if you push this in this way, so you can imagine your frame will try to move in this way, right? If you push this, right? So that means asymmetric loading configuration. If even without any lateral forces, asymmetric loading. Okay. The next thing is so let's say this is I and this is 2I and this is 3I. So this frame will sway even if you are at the middle. Why? This has relatively a lower stiffness than this, right? This is more prone to be moved, right? In such case, asymmetric, so even the geometric configuration, something like this, even you are at the middle. So this length is short, right? So it can influence sway. So this is truly asymmetric geometric configuration, right? Lateral forces, asymmetric loading, asymmetric geometric configurations, and another thing is support settlements, right? If your frame is like this, just think your support is settled. So support this support is going to settle. So that's going to be it's going to be like this. So there will be a horizontal delta, right? Horizontal deflection. So even the support settlements, right? So now, so okay, right? So these are the major points. So there are several, so there can be two or more combined, right? Sometimes everything combined. So those are also sway frames. right? So these are individual factors. There can be sometimes 2 or more, 3 combinations in the same thing, right? Right. So this is kind of a preliminary check, right? So if it is allowed, so this will only move if it is allowed to move, right? Otherwise it is not, right? So but in the support settlements, even if it is not allowed to move, support moves, right? So that we cannot do anything, right? Here, if it is not allowed, even with lateral forces, asymmetric configurations, asymmetric geometry, it will not move, right? So there's a link in everything, right? So first thing is this, right? This should be a preliminary check. And then if lateral forces, if asymmetric loading, asymmetric geometry, those should be checked, right? So that can be a sway influencing, right? So the next thing is you need to figure out what kind of, so if it is a non-sway of sway, right? Say, let's say this is frame. So this frame is allowed to move so you can see, wait a minute. So this length I will take L. Okay. Yes, I will take L. No problem, right? No, I need to give a value. W square, I say it is 6. So this is 2 kilonewtons per meter squared, right? This I would say 5 kilonewtons. This I would say 4 kilonewtons. Okay, so then this height would be 4 meters, and this is also 4 meters. And I would consider this is 2I. This is I. Okay. So there are several factors. It is allowed to move, right? Why? Here the horizontal degree of freedom is not restrained. It cannot move in this way. It can move in this way, right? And there are asymmetric geometry. There are asymmetric loading, as well as the geometry is also asymmetric, right? And the members are also asymmetric to I, right? So definitely this is a sway frame, right? So what can you do is first we need to make it non-sway. Make it non-sway. Why you make it non-sway? So the first thing is you have bending moment due to loading as well as bending moment due to the settlement. Sorry, actually the displacements, right? You can't actually work it out in, you can't work it out simultaneously. So we need to separate those. That's why, right? Even we don't know the value of delta, right? We don't know the value of delta. It's not given, right? So in that case, we cannot really do it, right, without separating. After separating, we can solve for each and finally superimpose to obtain the final structure. That's what we are doing, right? So we basically stop this way. So how are you going to do that? Is I will apply an imaginary roller in this way, right? Why a roller without a pin? Because if I apply a roller, I know that will only give one reaction, right? In which way? In this way, it will go give a reaction. If I apply a pin, it can give a reaction in this way as well as this way. I don't need that because that becomes more complex then, right? So I need to find that as well. That's additional work. I don't need that, right? So what I'm going to do is I'm just applying a vertically mounted roller, right? Why? I need to just restrain this horizontal movement, right? So I would say it will apply a Q force to stop sway. Now we make it non-sway, right? So, but now it's no longer the original frame, right? So it's like this. Right? It's no longer the original frame. Right? So the difference is I just apply a Q force in this way. That's what we only did to stop sway. So I will take this frame because this have all the loading. I will take them without the loading. Right. So the original frame, right? So just apply a Q force in this way at this node, right? Just apply a Q force. So if I, so I did was I took the primary skeleton, so I apply a Q force in the other way. So if I add these two structures, Q will be getting cancelled, right? So loading is same, right? So here do not have loading. If here also you had loading, loading will be doubled, right? So here you only have the structure. It's like you have common structure, and from this you have the loading, right? And this Q and Q getting cancelled, you will obtain the finally original structure, right? So now this is Nonsway, right? This is Nonsway. So we can easily solve that using moment distribution, and this is sway isolated. So we know there's some Q force which contribute to sway, so we isolated that into this sway frame, right? So we isolated the Q force into this sway frame. Why? We can then easily analyze it only sway without any loading. Here all the loading are here, and we can analyze it under static conditions with because it is non-sway, right? So we will apply this, analyze this first condition, non-sway frame, and then the second condition, right? So for the first condition, I need to consider what are the stiffness of this, right? So in the moment distribution video, I'll explain it is everything, right? So very precisely. So if it is here, it is discontinuous, right? Right, because you have only one member connected, right? So it is discontinuous. Here it is continuous. Here it is fixed, right? So here the stiffness would be for EI. So E is not given, so that means E is same, I is just I over 8, right? Here it is continuous to discontinuous. That's going to be 3EI over L. So I is given as 2I. Length is 6, right? Length is 6, and that's going to be how much? That's going to be just EI, right? This is going to be just 0.5 EI. Right, 0.5 EI and EI. Okay, so now my stiffness, okay, right? I need to find the distribution factors, right? So at here, it's a fixed support. Here it is a fixed support. Here it's a fixed support. So that I know distribution factor is 0. I have already explained everything at the first step. So here distribution factor is 1. So that means whatever bending moment is applied, this member have to take the 100%, right? So here you have two members, so that each will take some amount. That's the distribution factor, right? So if it is A, B, C, so distribution factor B. So this is called distribution factor at B for BAB. So if it is DFBA, so that means distribution factor at B for BAB, right? The first letter is important, right? Then it's going to be, so the stiffness of BA, so stiffness of BA is equal to stiffness of AB, but distribution factor BA is not equal to distribution factor at AB. Distribution factor BA and distribution factor BA and AB are not equal, but stiffness BA and stiffness AB are equal, right? So AB plus distribution factor BC. So that's going to be 0.5 EI, and here EI. So it's going to be how much? 1/3, right? So df, so that means 1/3, around 33% will be taken by BA, and the remaining 66% will be taken by BC. So this is because at a join, the distribution summation of distribution factors equal to 1. So there are two only, right? Once you determine this, you can just subtract that by 1. So it's going to be 2/3, right? Then I need to consider the fixed end moments. So here I have some loading. So definitely this UDL going to bend this beam in this way, but this axial, so sorry, this point load is going to act as an axial load for this member, right? So it's not going to give any bending moment to that beam, right? As well as since it is acting at the end, right? So if you, so fixed end moments are what happens if you fix the ends and apply the loading. So if you fix the end and apply this kind of loading, it's not going to give any bending moment, right? It's just the support takes the whole load, right? Beam does not take any load, right? So here it's like this. If you fix it and apply a load like this for this member, nothing happens, right? Nothing happens, no fixed end moment. So load is axial and beam will not take, right? So, but if you apply a load like this, so definitely there will be fixed end moments, right? So if you apply somewhere in between middle like this, so definitely this is going to have some fixed end moments, right? Definitely it is going to have, right? So in such case, we need to determine what are the bending moments, right? So we can determine this. That means this is not needed to fix end moments. So if this is 2 kilonewton and 6, so we take clockwise positive, right? So here it's given as clockwise, okay? So I will just write. So this is going to be W L squared over 2L. So the value is W L squared is 36 over 2L. So that's going to be 6, right? So here the same value but negative, but here we have drawn it in the anti-clockwise direction, so it's anti-clockwise 6. But if you draw it clockwise direction, it's -6, right? Okay, here the direction is shown correctly, right? So then you need only the magnitude. Here our sign convention dominates clockwise positive, but the value should be -6. So that means magnitude is 6 and the direction is anti-clockwise, right? Here it's also, if you provide like this will be clockwise, right? And this will be anti-clockwise, right? So this value is going to be PL over 8, and it is also what is P? 4 kilonewton, right? This is not going to do anything, right? So it is 4, L is 8. So that's going to be 4. This is also anti-clockwise 4, right? It's clockwise 4, right? So now I can write. So I know the distribution factors. 1/3, 2/3. It's okay, right? So I will write now the table. This is B, this is C, this is A. So at A you have AB, at B you have BA and BC members connected. At C you have CB, right? So basically your distribution factors are A is fixed 0, B is BA was 1/3, so that's going to be 0.33. This is 2/3, so that's 0.67. Here it's 1, right? So here it's a fixed support, so you know sigma, M is not equal to 0. Here B it's a continuous support, so you know sigma M should be 0 because 2 or more members that has, right? Okay, so right, so here it's a discontinuous support, so that means it only have one member and that member moment is 0, right? So final sigma M is the both two, right? The summation of BC and BA moments, right? So you have fixed moments as here it was -4 +4. Here it was -6 and +6, right? So I will first balance CB, balance C joint. So here you have +6, so that means it's and clockwise bending moment is remaining at that point. That means it's like this. C joint is here, right? Clockwise moment is there, right? So that means you have a additional bending moment, right, which is not unbalanced. To balance this, you should need to add an anti-clockwise moment of 6, right? Anti-clockwise means negative, so that means you need to add -6, right? So you need to add -6 to balance that. Okay, so once you balance it, you consider carryover, right? So what is the moment carryover due to the additional applied, right? So that is the induced bending moment at the next end. So carrying over done within the same beam, the same neighborhood as we discussed earlier in the videos, right? So CB's neighborhood is BC. So it carries, so it is discontinuous to continuous. So it should give half, right? If it's other way around, it does not give continuous to discontinuous, nothing is shared, right? So here it's giving half. Always carryover factor is half, right? So here, yes, it's 3. Now I don't need to do any damn thing on A joint because that's a fixed end. So distribution factor tells you you share 0 here, right? You don't need to do anything, right? So I will start then balancing B, right? There you will remain how much? It's -9 plus 4. So that means the additional is so -9 and plus 4. So you will be remaining -5. So that means anticlockwise 5. To balance that, you need to have clockwise 5, right? To balance. To balance. So to balance, you need to add 5. So that is going to be distributed to each member. So BA tells, okay, I can take 33% of that. VC telling, I can take the remaining 67% of that. So 5 into 33% means 5/3, right? So that's going to be how much? That is going to be 5/3, 1.6, right? Seven. So the remaining part is going to be 5 into 0.67. It's 3.3, right? So now my condition is satisfied. M is final. The total moment is 0, right? So when you add these, you will get the final moment. Final, sorry, not the total, but final, right? So final moment. So don't add distribution factors. Don't add this, right? So 6 minus 6, it's going to be 0. Here it's going to be -3. Sorry, -9, -9, minus 0.33, right? 33 -9. So it's going to be -5.6, right? Here it's going to be 5.67. Here it's 5.66, right? So you can see the summation is 0, right? So that condition, okay, here bending moment doesn't need to be 0. So one more thing. So I'll stop at from the balancing step. If I needed, I can carry half to this, okay? I can carry over half, but it's usually better to stop at a balancing joint, right? Balancing step. So since if you balance this, you don't have anything remaining, right? So I will balance that as well. So I will carry over because that's the final step, because this is not repetitive or not converging, right? So you can just carry over, but make sure you stop at the balancing step. That's a good practice, carry over. So this is continuous, fixed, right? So that shares half point. So neighborhood BA's neighborhood is AB, right? So that's continues to fix, that show that give half, right? So your final bending moments, so it doesn't matter, right? It is considerably low value, so it's going to be minus 3.17, and here for 5.6667 positive. This is minus 5.66, and here it's 0. Everything is 0. This is non-zero. The summation is 0. Here it is 0, right? So these are my final bending moments for the non-sway frame, right? So I need to analyze now the second one, the sway frame, sway isolated. Here I will take, if I apply delta here, right? So here there is only a Q force, right? Right. So one more thing need to be done here. I need to find the Q force. That's essential. So I will do that as well. Since you know the bending moments, you can find that. Q is here. I would say this is R, C. This is R, A. Right. This is, I would say this is H, A. Right. It's a fixed and it has some bending moment. So that bending moment was estimated earlier. How much? Minus 3.17. That means anti-clockwise, I would say 3.2. I don't need to drag minus because I just consider the correct side, correct direction. And here the force is how much? 4 and 5, right? So I know all the bending moments, right? So here bending moment was plus clockwise 5.68. So that's clockwise. Here it was anti-clockwise. So that's going to be 5.66 around, roughly. So here it's 0, right? Because it is a pin joint, right? So pin or roller, whatever, right? So here it is 3.2. So I can consider the horizontal equilibrium of forces, right, is equal to 0. So that means HA plus 4 plus 5 plus so HA plus 4 plus 5. Let's see, only no, here we have, these are the horizontal forces. You have HA, then Q is equal to 0. So to find Q, you need to find HA. What is the easiest way to find HA? So things always logically. So if you take a bending moment about this point to this member, you can easily find HA, because this RA is not coming, is the only unknown. HA is coming, 3.24. These values, you know, so you can take bending moment about B for BA, right? It should be 0 sigma. So that's going to be 5.66. This moment, this force is not coming. 4 into 4, right? That's anti-clockwise direction, right? So it's going to be again anti-clockwise, right? This is going to be anti-clockwise. So also minus 3.2, right? So HA is also anti-clockwise, right? Into how much? The length is 8. 0, right? So when I simplify this, it's going to be 5.66 minus 16 minus 3.2 is equal to 13 point minus 13.54, right? So that's going to be the other way around, right? So I put this term the other way. So it's going to be HA into 8. Right? So HA is going to be how much? HA is going to be how much? So if you divide it, HA is negative 1.69, right? Minus. So I would say it is minus 1.7. So if I apply to this equation, it's going to be 9 minus 1.7. So your Q value is 7.3, right? This is the correct Q value, right? This is the correct Q value under your external loading, right? So we found the Q value, right? And we just need to, so here we know this is Q is 7.6, right? 7.3. But the problem is we don't know this delta, right? How much it settles. So usually the fixed end moments are governed by this equation. Fixed end moment is 6EI delta over L square. Problem is we don't know the value of delta, right? So this delta will depend on the Q, right? We don't know the value of delta, right? This delta will depend on the Q. We don't know the value of E as well, right? So if it is not given, we cannot find delta, right? So that means we can assume a delta, right? We can assume some value to delta. So the moment you assume, because we need to make this something which can be simplified, So I will again draw it. So This is your final frame. So that has gone delta. So this is just a rigid body motion. So this is going to have some fixed end moment, right? Due to these laterals. So if you apply like this, so this is going to be deflected like this. So this is going to be just laterally moved. It's a rigid body motion, so they don't have any fixed end moments, right? So, but this will have, right? Remember, if you support settled like this, a delta, there will be a fixed end moment, right? So this has gone down, so that means it should here way. So it has gone up, so that means in the other way, right? So that is 6 EI over L squared, right? So the problem is we need to find the direction. So here I will tell you a convenient way. Think always relatively. So compared to here, this member has gone in this way, right? So what should this point do to take it back? To take it back, he should apply a bending moment in the other way. So this is my fixed end moment. So compared to this joint, right? This part has moved in this way. Can you see? Relatively, it's always relatively. Doesn't matter what actually settles, it is relatively. Okay. So compared to this frame member has here, this part has moved in this way. So to take it back, he should apply a resistive moment in this way to take it back, right? So this is your fixed end moment. This is your fixed end moment. The value is here, right? So you can just, so it's the same value, right? So 6 EI delta OL squared. So you can substitute 6 EI, I is I, delta is delta, and L is how much? 8 squared, right? So I can just consider this is equal to 100, right? This is the assumption. This is the assumption I take. Why? To simplify, right? If I can take this into a moment distribution table, I can easily simplify. Even if you need, so this is your Q, right? Q is actually 7.3. Let's say this will have a value of actually 0.01 actually, right? So we don't know the value. The problem we have is we cannot simplify this term in the moment distribution table. Why? Because we don't know this value, and here as well, right? And here, because we have given only the letter, right? Letter notation, right? So if you applies 100 equal to this 100, so this might take some arbitrary value, right? Let's say it can take, I don't know, it can take 0.2 depending on these values. Okay, this will have 0.5. We don't know this value. We don't know, right? So only thing we know is delta is not actual value. If it is not actual value, right? Let's say this is the actual value, right? This is also just to teach you, right? So this, if this is not the actual value, what can you say about the q? The q you get from the system is not the actual value. It depends. So if you apply 1000, it will give, so depending on delta, it will give q. So that means if your delta is 1, q will be q1. So that will give some value. If your delta is the actual value, so if you calculate it, it will give q as 7.3. So if your delta is something around 100 or something, right? Q will be another q. Let's say q3 or q2. So likewise, depending on here your assumption. So this assumption is why to simplify the table, right? Without knowing delta, we cannot simplify the table. You will see that, right? So even if you want, you can assume 100, you can assume 1000, but if you assume 1000, it will take more time to converge the values, right? So that's going to be not easy. That's not going to be easy, right? So that's why I'll assume 100. So I can, even if you want, you can assume 10, right? But if you assume 10, at least go for one decimal place or two, maybe two. If it is 100, I can definitely go for one decimal place. That's it, right? So if you need, you can take 50. That's okay. You can take 5, whatever value, depending on that value, you will receive. If you finally solve the structure, you will get another q value, but it will give you only the correct q value if you apply only the actual delta, but we don't know the actual delta. That's why within these huge number of range, so it can go to plus infinity, we will assume something. So even we don't know what we are assuming, we are taking the whole thing is equal to 100, right? Because we don't know what is e, what is I, right? We are assuming the whole thing is 100, so that we cannot tell any one of it, right? So if we assume it 100, right? So this table is going to be A, B, C, A, B, A, is in. So we solved the moment distribution part for non-sway frame. This is for the sway part, right? Sway isolated, right? CB. So we know we only have a fixed moment in this member. Here we don't have anything, right? It's just rigid translation. Since this is relative in horizontally displaced, so it will like this a support settlement, right? Just like that, idealize the behavior, right? So if you have something like this member, this will also be will be displayed and have fixed moments, right? But the direction, I think it's going to be always anti-clockwise according to this, right? So you had 6ci delta y square, so that we equate it to 100. So but we have anti-clockwise, right? So actually it is minus, so that's going to be minus 100, right? So we have 6ei delta y square. This is the value. So I took this part. Don't please take it without the sign, then it is more easy. convenient because you know actually the direction is right. So it's 100. So this is going to be minus. So this is going to be minus 100. This is going to be minus 100. So first I need to write the distribution factors. So you need to start everything by distribution factors. It's 0. Here it's 0.33. Here it's 0.67. Here it's 1. So the fixed end moments those are minus 100 plus 100, 0. Here rigid body translation, the member BC, right? So nothing happens to that. If you have some vertical member like that, this will also have fixed end moment. This have also fixed end moment. This is just rigid body translation, right? This is delta. This is also delta, right? So yes, I'll start balancing B. Because to balance C, I don't have anything. Balance B. So that's going to be 33%. So I need to add. So there's, so sorry, this is negative. So both negative, okay, both negative. So it has an anti-clockwise 100. To balance that, I need to add clockwise 100, right? So that means positive 100, I need to add it, right? So because positive is our sign convention for clockwise, right? So positive I have to add. So this will take 33% and this will take 66%. So 100 into 33 means 0.33 means it's going to be 33 and it's going to be 66. So the carryover part. So if it is BA, it's continues to fixed. So BA's neighborhood is AB, always carrying over done within the same beam to the neighborhood. If it is PA, it's for AB. For AB, it continues to fixed. It should give half. So that's going to be 16.5. Here, BC to CB, it's going to be continuous to discontinuous. It's not giving anything, right? It's not giving anything because it's continuous to discontinuous, right? So carrying over is not done. So BC's neighborhood is but CB, right? So I can take the final bending moments. So here it's going to be how much? 100 minus 16 means 84. So that's going to be 83.5. This is going to be 100 minus 3. So it's going to be 67. Sorry. Minus 67. This is going to be 66. It's going to be 0. You draw it. So you have a Q force in the other way, right? So this, so now we change, so we assumed something, right? So the for the moment, from the moment we assumed, we don't know what Q value we will get, right? Because we are not inputting the actual values, right? So we assumed it for our convenience and we will get some Q value, right? Let's say I will get a Q dash. So my forces are 83 point, so this is negative, okay? So it's in this way, 83.5. No any forces. So this is negative. So I would say this is 67, 66 for convenience. I'll take that both equal. So here it's 0, right? So here you will have some reaction R C dash. Here you will have some reaction R A dash, and you will have some vertical reaction H A dash. This is a completely separate system, right? So you need to find what's again you need to find Q, right? To find Q, I will take sigma F in horizontal direction. So that's going to be Q dash plus only this was minus HA dash is equal to 0. So that means if I found HA, that's game over, because Q dash is equal to H dash A, right? So to find Q, the easiest way is take a moment around B for BA beam. Moment around B, sigma MB for BA member, right? That should be 0. So that's going to be 66 in, sorry, I think I did wrong. This is anti-clockwise, right? This is clockwise. I think I did this as well. This is clockwise and this is anti-clockwise. That's correct. That's correct. Here it's anti-clockwise. It's clockwise, right? So anti-clockwise is so minus 66, right? Minus 66. And this is minus 83.5. So since we are taking around this joint equilibrium forces are not coming. So this RA is not coming, line of action through this point, right? So only this HA is coming, that is going to be clockwise. Into 8, the distance is 8, right? So you can just consider what's the value, 66 and 83.5, the summation is 149.5, so you can divide it by 8. So that's going to be that's going to be how much? 18.68. So I will consider this is, so we are getting the Q dash is this, right? So was my Q value was correct at the end? That's right. So the correct Q value is 7.3, but according to our assumption, we have got a Q value of 18.6, right? So these values are for if these values are for a Q dash, what will it be for original Q? So we just need to, if X, Y, Z, so we need to just normalize it. So that means divide it by Q dash and multiply it by original value. If it is for Q dash, how much it will be for the original force, because these are linear, right? Right? Delta and Q are linear. You remember the assumption? So y is for q dash. What will it be? It will be for q. So from this, you can take the final bending moments MAB was here it was minus 3.17. This is from the Nonsway frame. MBA it was 5.67. MBC MCB was 0, right? This is from the Nonsway. We stop this way. Nonsway, right? We stop this way. Why? We can then moment distribution using the external loads and everything, and we isolated swing separately, right? So we then just need to add. So this adding means we are superimposing but these two, we found this is an Nonsway frame. We are superimposing these two structures. Once you superimpose, this q force will be cancelled, right? But these q values, so this is the original q value, right? These are for the original q value, Nonsway frame, but these sway isolator, sway frame, those values are, so here it's 83.5 negative, right? 83.5 is for a force of 18.6, right? So what it will be for the actual q value? Actual q value was 7.3, right? Just need to multiply it by 7.3, right? So it's like you can take this to under the q force actually. So you can just write it as, here it was minus 66, right? So you can just its correct q value over the assumed and obtained q value, 18.6. So this is 66 into 7.3 over. So this is anyway 0. So the final values would be how much? So the final values are, so 7.3 over the ratio is 18.6. It's going to be 0.4, right? So we need to multiply these values by 0.4. Plus 3.17. So this is going to be around minus 36.6, right? So this is going to be This is going to be 20.7. So this is minus 20.7. Okay. So this is 0. So these are the bending moments at the joints for the final structure, right? So you can just draw this, right? So this is minus 36.6. So I'll apply a anti-clockwise bending moment like this. This is also anti-clockwise. This is clockwise. So that value is 20.7. And here it's going to be going to be 36.6, right? So this is the final structure, right? Here it's 0. Okay. So yes, you can draw that value on the side where it's shown by the arrowhead. So this is telling you should draw in the lower side of the member. So that's going to be 20.7 something. So it's showing for this member. It should be in this way, 20.7. So 36.6, the arrowhead showing in this way, not this way. It's 36.7, right? So this should right. So this is your support bending moment diagram, right? So but you have some simply supported loading, right? So that you have something like this and something like this, simply supported, right? So I told you this load is not going to affect, it's acting directly to the joint and it is acting axially to this member. So neither members would have an bending effect due to this force, right? So this is how much? 4 and 2 kilonewtons per meter squared. So this is going to be PL over 4. So that's going to be 4 into 8 over 4. And this is WL squared over 8. Right? So that's going to be W is 2. L squared is 6 squared over 8. Right? 36 into 2 means 90. So there's going to be 9. Sorry, this is going to be 8. So I told you these are sagging bending moments, negative, right? Sagging, negative, right? So support moments are usually called to be hogging, right? So never mind. So usually, right? So it cannot be the other way around, right? So here you can see actually it's at the support you have sagging, but don't get confused with everything, right? So it's at ends you have 0, at here you have 9, at ends you have 0, here you have 8. So you just need to go and replace this. So for this member, you have a curve, right? At the ends, it is 0. It's not going to affect anything. but at the middle you have 9. So the middle value is 20.7. I would say here it's the middle value, I would say 10.35. So from that 10.35, I need to minus 9, right? So it's already in the negative side, already in the negative side. So load is acting also in this way, right? Negative side. So I need to add this value, 10.35 into 9. So that's going to be around 19.35. Right? So here as well. So it's going to be at the middle, 36, 37. So that would be, so I can't, you can just, so this is minus 20.7 and this is the other way around, plus 36.7. So it's around 8 point something, right? It's around 8. So you have to yes, you have to subtract that value, right? So because the load is in this way, right? So it's 8 something, right? So it's going to be here. So you can see compared to this value is relatively small. So your significance is lower, right? So that's a straight line, okay? So your final bending moment value would be like this. So this part is not now actually reducing, so that's adding. Why these are also drawn on, all things are drawn on here for this member in the sagging part, right? So and for this member, you have something like this. So this part is cancelled. This part is cancelled, right? It's negative and positive. It's, this part is cancelled, but this part is coming. Right. So you have some, for the other member, it's underneath that, right? So that part is going to be like this. So those are not cancelling because it's separate members, okay? This is for the horizontal member, right? So yes, thank you. So, and you saw what we did, right, actually. So what you need to do is actually, so the first thing is determine sway or non-sway, right? Then if it is, if sway, so no, I can draw it like this. So just consider you need to do a sway, like there's a frame, right? So you input that. So you have to determine if it's sway. If yes, if yes, in this way. If no, you can use moment distributions directly. And solve. And you are done, right? If it is yes, if it is sway, right, you need to divide it to two parts. So make it none sway. Make it none sway and use moment distribution. So this is moment distribution, okay? Moment distribution. Use moment distribution. Find Q, sway force. Original. Right? So here you isolate sway. So you isolate the sway moment only for that frame. Isolate sway. Right? Isolate sway and so for the U delta, EI delta or something, the part you don't know, assume something. Assume something and then use moment distribution method. Right? So then find. So since you assume something, that would give you something Q dash different. You don't know the value, right? Again, so delta and Q are proportional, right? So if you delta is 1, it will get Q1, right? So delta is some value. So if it is the correct value, it will give you correct Q. We don't know the value of delta to get the correct Q value, right? So we will assume something. So if it is 100 or 1000 maybe, right? Anything, any value that can give any value. Q4, this is Q3, any value, right? What we know is that is proportional, linearly proportional, right? So once you find Q dash, right? So convert moments. How to do that? So moments are for, if the moments are for Q dash, but it will be for Q. If the moments are for Q dash, but it will be for the original Q. right? This is the original Q. This is the Q dash, right? So finally, the moments you take from this and you superimpose it, right? So solve it. Right. So this is bit tricky, but this is the overall picture, right? If it is non-sway frame, you can see it's just one step, right? It's just one step. If it is sway, so you have to isolate the sway everything. So here you isolate the loading and everything with non-sway frame because it's easy to analyze then. And then you move the sway part to the uh, to just frame, right, without any external loading. From there you can analyze sway, right? So for that you don't know the delta, you assume that and use moment distribution. You find here the correct Q value, you will obtain another Q value but not the correct. But then you can find the bending moments correspondingly and then convert the bending moment value. So if you are getting m dash values, right, so you just need to divide it by the Q dash and multiply it by the original Q value. Original Q value is there, then you just take those converted values and from the first structure and the second structure and you superimpose it, you solve it, right? So this is the summary. So thank you very much.